So the process that they use is applicable in more than just 3 dimensions. You couldn't do the cross product the way they did, but there is cross product in higher dimensions, believe it or not. It's just called something a little different. So you could do this process in higher dimensions. The process we're using also, actually, well, if we do it like this, if you guys, I know a few of you guys have used some vectors before. Gallo 0. I mean, what we've basically just done is we did row 1 minus row 2. Is that cool? I don't know if you guys have at least done this much, right? Row reducing. So 1, 2, 3, 1. And then, actually, let me do this. Gather. I'll do exactly what we did. Yeah, that's fine. Row 1 minus row 2 and put the answer in row 1. So we have 0, 3, 2, and 0. I like it. And then we got 1, negative 1, 1. The reason I do that is because we kept this one. That's the nicer one with coefficients of 1. So that's the other equation. I kind of want to keep it. It would work either way. And how many of you guys, now if I keep going, I can keep going, and I can say 0, 1, I can just multiply this by 3. Is that cool? To continue. So I get, leave this one alone. And then this would be, oops, yeah, there's 3's. All right, 3, negative 3. Oh, they were almost all 3. So this will be, oh no, I gotta go the other way. All right, so you can do it. You can do it. I gotta kill this one using this guy. That gets gross, but too bad for us. Oh. You guys, I don't want to go this way because I would kill that.
You divide by 3, right?
So if I can put the answer there, that's right. You can do it, John. So if I put the answer here, so it'll be 3, negative 3 and 3 is 0, 3 plus 2 is 5, 3 plus 0 is 3. Now I don't know if you guys know, do you remember going further than this? I mean, how many solutions would this have? You can't get all the way, it doesn't have enough to do all the way anyway. So you'd say 3y plus 2z equals 0. And you'd make parametric equations out of the results, right? You'd call, in this case, I would call z t and go from there. We sort of did that. We stopped a little bit early, but we still could kind of force feed things back in, get to an answer. So if you do it over there, you get the same answer. It won't look the same because I can multiply these by whatever I want to. But that's another way to do the same thing. And you've done this before. You just didn't know what you were doing at the time. Please tell me, have most of you guys done this kind of thing before? Has anybody never row reduced a matrix? It's okay to say you haven't if it's true. You guys are like, I ain't telling you shit. All right. But if you have, it makes a lot of things make a little more sense. Especially when you look back down, you say, if we let z be t, I get... Because I don't have enough information to make a single answer. But I do have enough information to make it a plane of answers. Or in this case, a line of answers. All right. So yes, you could do this the same way in the book. What would this look like? This is almost the same problem as the one in the book. What's the normal vector for this guy?
1, 2, 3.
1, 2, 3. Normal vector for this guy?
1, negative 1, 1.
Take the cross product, because now you understand that the intersection of those two planes would be a line that is in both planes, therefore it must be perpendicular to both of those normal vectors. And I really want this to make sense, as always. I don't have to worry about how long that resultant is, because it's just a direction. The direction doesn't have to be a unit vector. That v in this equation, does it have to be a unit vector? No, it does not. It does not need to be a unit vector, because I can control that with t. I can get every point in that line by picking any value of t. I don't need the v to be a unit vector. So I don't know if anybody, when you cross these two, you're going to get something that actually includes the magnitudes of those two, and the result's going to be its own magnitude. You don't care. It's the direction you care about. So you can do this problem the same way the book does it, or you can do the problem a little more old school, the way we've actually done it before, if you've done any of those row reducings before. You got answers with infinite solutions. Hopefully your teacher pushed you and said, don't just write infinite solutions. make parametric equations out of that. Hopefully, maybe. If not, you don't have to do it that way. Do it the way the book did. The way that we discussed in this class, using vectors. No problem. The big thing to realize here is that's the key to this problem. Because like we said earlier, the line's got to be in both planes. I like it. Maybe. Yes, sir?
Yes, since those are the normal vectors, the vector perpendicular to both of them is going to be the linear vector.
Yeah, so if you think about it, any vector perpendicular to this vector is where? Any vector perpendicular to this vector is where? In this plane. In that plane. So if I take the cross product, the result is how related to these two?
It's
Perpendicular to both.
Which, if they
Therefore, it must be in both planes. That's almost too nice to believe. Right? Some of you guys are like, you lost me at hello. Shit. That reference still holds. I like that. All right. It's a long time ago now. Okay. All right. Anything else specific from 12.5? Or even slightly general? Yes.
Oh, so you're good.
So far, pretty good. Yeah. Thanks, man. Care about me. Oh, yeah. Yes, Jeff. Your mental health directly affects my grade. Yeah, I might go crazy, give everybody an A. You never know. You don't want to chance it. All right, guys. So if there's no more direct questions, we're going to get into chapter 13.
Are we skipping
12.6. Didn't I basically say? Well, all right. Let's take a look at 12.6. Yeah. I like that. Last. Let's see. What's up? All right. The main thing with 12.6, and yeah, I did talk a little bit about this, right?
Yes.
For sure I did.
Yes,
we did. I did. Sorry.
It was brief, it's fine, I forgot.
I forgot also, and I was like, oh shit, I meant to. And
Yeah,
then
no,
it
you
came
did.
back to me.
I remember
So,
looking at the pictures.
this is where I made the big push to, and again, I have no part in this company. I wish I did. But, and there's other ways to do three-dimensional graphs, but Wolfram Alpha, to me, is the most intuitive, and it makes it very easy to see the whole graph, the 3D graphs, to be able to rotate them. I wish back in my day I could do that. My instructor drew worse than I did, and he was trying to draw 3D. You can imagine how that didn't work. Anyway. So if you get Wolfram Alpha, you can actually plug in your own function, you can rotate it, you can enable interactivity and rotate the bad boy. If you have rotation, you get to see what the hell the whole thing looks like. The big thing with 12.6 is this idea of traces. So if I wanted to draw the trace of this function, oh, let's see, what kind of a function I want to use? Sure. What would that trace look like in the XZ plane? Perpendicular. How do you know that?
It has the
To be honest, it's a little bit of a trick question.
bases are different. 3 and
The little bit of a trick question would be
Because they'd be subtracted if you set it to 0.
exactly. If you set y to 0, though, what happens? I mean, then you get so this will be y equals 0. Why does y equal 0? Because to get into the XZ plane, you need y to be 0. And this is why traces are so nice, because then you can just focus on 2D for a minute, And they kind of help you envision what it would look like when you put them all back together in 3D. So if y is 0 and you pull it over and you get z squared over 9 minus x squared over 16 equals 0 though. So what you really want to do maybe is 1 up from the xz plane. So that would be where y is 1. Right? So in y, actually let's just do, on the xz plane, what would this be? What would this look like? Equals 0. So really that equals that.
Point.
Sort of. So you get z over 3 equals x over 4. Is that cool?
Oh,
And that is a line. I like it. So what's really cool, if I wish I would have thought of this, there's a cool animation somewhere online where as hyperbolas, as you're doing this kind of CAT scan through a 3D object, the hyperbolas that are kind of like on the side of the object get closer and closer together, until they're just crossing lines. Right? Crossing lines are sort of like an extreme of end of a hyperbola. Yeah.
If you think of it as like the cone thing, because they're conic sections, if you have two cones that are the same but like they're meeting at their points, and it's a hyperbola is when you cut it vertically, and if you move it to the center, then it's just two lines.
Exactly. Then you get those two lines. So that's a nice. Another way to think about it's just an extreme position for looking at what happens to a hyperbola when you let this guy go to 0, for example. So then you can say, okay, that's nice. So those are intersecting lines in the xz plane. If you looked at it up 1 from there, then you do get a true something. If you let y be 1, then you get a true hyperbola. Right. If you let y be 4, what would happen?
A bigger.
True, but so this is nice because then this will be z squared over 9 minus x squared over 16 equals 1, and the 1 is key, right? If I let that guy be 16, I'm going to have to, if I really want to do it old school, I'm going to have to do what?
Complete square.
Divide by 16, which makes these numbers bigger, so on their axes, what happens to my points? They get closer to the origin or further away from the origin? Further, because these get bigger, and that's the distance from the origin, right? Or from the center in general. Maybe. This is the kind of thinking you have to be able to employ. But do you see what I'm doing? I'm not just doing standard traces in XZ. I can also do traces in a plane parallel. And this is a beautiful situation to do that in, because in 0, it's too specific. It's some extreme case. But -1 or 1, now I've got, and of course you realize this is plus or minus 1 really, of course, right? So it's somehow symmetric in both directions around the y-axis, right? Okay, maybe. Around the xz plane. Maybe stop there for a second. Okay, so that's the idea of traces.
It doesn't quite seem to be right with the picture.
So this one we're doing is this guy. So you can see the x.
That guy. Okay.
What's up?
I thought it was the other guy.
Oh, no. Oh, yeah, no. I picked this guy. My bad. This guy here. So we get a nice cone going on. Cool. Now, of course, you can see it's really easy to see what's this shape going to be. I mean, currently it looks a certain way, but we know it's going to be a circle. And that would be looking at the xy, letting z be 1, 2, whatever. It's actually going to be ellipse here, yeah. But if these were equal, then they would be a circle. So it could be a true ellipse. I like it. So maybe. But you guys get the feel for, this should be semi-familiar. You let a variable equal certain values and you see what happens. I mean, that's what you do ever since the beginning of algebra, right? So here we've got 3 variables, 2 of them independent, 1 of them dependent. And you can look at any of them as being the dependent one, really, and you just let something have certain values and see what the other ones do. So this is investigating slicing. Let me slice it this way, to the xz plane. That's what I started doing here. Let me, if I want to slice it next to the xz plane. Then I can slice it near the yz plane, slice it near the xy plane. So those traces are normally referred to the standard xz, yz, xy planes. These are like even more slices parallel to those planes. I like it. Yes, sir.
It's like an MRI.
Yeah, MRI might be better. I said CAT scan, but I think MRI is the one that kind of goes layer by layer. Okay. So here's some traces, and you can see, now this is kind of cool. This is what I'm doing right now. Y equals 0. There's k equals 0. K equals 1, so let y equal 1. So I could actually do, in the xz plane, sort of, I can make a trace of what it looks like when y equals 0. It would be this line here. Right? It would be z equals 3/4 x. Right? Plus or minus. I left out the plus or minus. So it'd be bam, bam. Right? And then so that would be k equal to 0. K equal to 1 would then be a hyperbola. K equal to 2 would be a slightly further away hyperbola. So forth. Right? Because if I let y get to be bigger and bigger values, it just gets further and further away from the origin. I like it. So that's an example of traces that aren't just standard XZ plane traces, but the nice thing is it's almost like a topographical map in a way. You guys have seen that topographical map where it's 2D, but they sort of show you the lines that say now you're 200 feet up and now you're 100 feet up. You're getting down the mountain. Yay. I like it. That's what this is capturing. That K is sort of like, how far away from that plane I am. Okay, maybe. Okay. So, this is you just got to jump into this because this is just letting certain variables, giving them certain values and just investigating what the results are. You just got to jump in and start doing it. The beautiful thing is, the minute you start doing traces, you're back in 2D. You all know how 2D works. So that's kind of nice to be able to start a problem off in 2D. And if I'm you, I'm always going to have something like Wolfram Alpha as a backup check to make sure that I'm looking at this correctly. Right? If you don't pay for it, you won't be able to rotate the thing. But at least I think it should still graph it for you. Just won't be able to rotate it. Okay. Any specific questions from 12.6? Anybody start in 12.6 yet? Yes?
I have a question on 12.6. Number
28?
Yeah, it was a really weird graph, and when I was doing those traces, I couldn't visualize it.
Alright, so let's take a look. 28. You can almost see that. So this is the one that says match up these with
Yeah. So you basically
ones
do a trace
below.
and then you find which graph corresponds with it.
So what do you guys want to start with? Let what be what?
Y equals 0.
Alright, so let y equal 0. Actually, to be honest, you could do this. If y equals, like you're doing k. So now you realize this is just some number I can put there, right? So if y is k, all right, now you realize what I have to be careful about the values of k, because fundamentally, what is this going to be, obviously? Hyperbola. I like it. And again, the larger k gets, the further it is away from the what plane? XZ plane, because k controls what? My motion along the y-axis, so I'm just getting further away from the XZ plane. And I can let k be negative. Now what happens if k is negative, though? So right now this is a hyperbola, and if I look in the XZ plane, for any specific value of k, let's make k equal to 1, just to make this nice, right? Which axis does this thing sit on? Yeah, the x-axis. Remember, it's the one that's positive, the one that actually has real intercepts, right? So it's going to sit on the x-axis, so it's going to, it's going to basically look like that. Blah, blah. Right? So for this is for k equal to 1. And for k equal to whatever, it's basically going to have that same shape. It's just going to, again, it's just going to go further out. Now, what about for k equal to 0? So see, this is k equal to 1. Yeah, k equal to 0 would just be lines, and of course this is really nice, it's just be lines straight through there. And then as you lift, it's going to separate like that. They just kind of come together at the bottom of this, or the bottom from that direction. Do you guys start to see how to get a feel for this? So if I look at the XC plane, it should be like the cross section should be these lines in the XC plane. And as I move away from the XC plane in the positive direction, it should be. Now what happens if k is negative though?
Circle.
So this is if, and this is why k greater is equal, if y equals k less than 0. Be careful now. Like what if it's negative 1?
Circle.
It's on the z-axis.
Be careful, you guys are... Yeah, exactly. You just divide everything by negative 1, so now they all just switch. Now it's hyperbola sitting on the z-axis. You guys see that? This is the exact kind of work you need to do to get the traces drawn so they can figure out what it's going to look like in 3D. Right? And don't make assumptions. Actually do the work. Otherwise, when you say circles, you're going to be like, none of these things match what I thought it was going to be. And then you can do, exactly the same thing with let x be a number. Right? Then what would happen? So if x equals k, what have I got then? K squared, but it doesn't matter. Just some number minus z squared. So that's going to be in the yz plane. What's that going to look like? Parabola. Opening down. Shifted by k squared, right? So whatever k squared is. And again, you could be more specific and say let k equals 0. If k equals 0, that gets... what is it for k equals 0? Y equals... negative z squared. That's just a beautiful, bam. So as you move away from what axis, then the parabola kind of shifts. As I move away from the axis in both directions, actually, because it's k squared, right? So I move away from what axis, though? What axis am I talking about?
The YZ.
What axis am I moving away from if I let this be 1? Sorry, this k. That's the x. So what am I saying? I keep saying the axis on. What plane am I talking about? The YZ plane. I like it. So as I move away from the YZ plane in either direction, then this parabola just kind of gets lifted up. So it's kind of like so at the origin, or at the how do I say this? Try to bring all this in at once. So here's the YZ plane. So it's going to look like this here, and then as I move away, it's just going to be a parabola that gets higher. But when I say higher, I got to be careful. This is in the YZ plane. You did this in the XZ plane. So in the YZ plane, it's going to be like this. And as I move away from the YZ plane in either direction, it's going to go up, because this is k squared. Even if k is negative, it's still going to be positive, shift up. So it's going to go up, up. I suck at drawing. So it's going to start here, and you're going to go up in both directions and be sort of like curved in that direction. So is anything looking like that? So we have, as I move away from the XZ plane, I know what it looks like. As I move away from the YZ plane, I know what it looks like. Do you see the way to look at this? And not only do the traces, but also think about as you move away from those planes, what does it look like? Is anything doing that? Any of these? Let me see if I can get on. So there's two things to realize. in what we've done so far, we haven't done all the planes yet. We've only done 2 of the planes we could do, and away from them. We've done the XZ plane, and we've done the YZ plane. But what we know from both of these, from this one especially right now, it goes in both directions around the YZ plane. It doesn't just, so some of these only exist on one side of a plane. This only exists on this side of the XZ plane, for example, right? Do you guys see what I'm saying? It doesn't exist on that side of the XZ plane. So that's something to watch for to eliminate some of these possibilities. So does this exist on both sides of the XZ plane? Can I let K be positive or negative? Yes, I totally can. So it exists on both sides of the XZ plane, so I can eliminate this guy. He doesn't exist on both sides of the XZ plane, so screw this guy. He's out. And then also the YZ plane, it exists on both, so is any of them. I think everybody else exists everywhere. It's too bad for us. But at least we eliminated him, right? Now, as we go out from the YZ plane, it's supposed to look like curved. So is anything doing that?
No.
Yeah, that one's a little bit freaky to try looking. Do I have them all up here? I'm missing some of them, aren't I? That'd be a little evil. There's some more down there. Yes.
Yeah, my biggest problem with this was drawing the 2D traces, and it wasn't intuitive to me what shape it was going to become. Versus the other ones where if you have parabolas and you have a gap, you know, it's 2 sheets, 2 paraboloids, you kind of have a good rule of thumb of what it's going to be. This one was kind of weird because we're getting the parabolas and we're getting an X.
So this here, this one is a little weird. Do you notice how it does go back? They've only drawn part of the sheet. I don't think they mean that it stops here. So that's kind of this is definitely contained, right? This is just a cylinder, so this one should be, what should be true about, who can tell me anything about this guy? What should be true about the equation for this guy?
There's no y.
Yeah, there should be no y, because there's no restriction on y. Y can be, wherever y is, the x and z does the same thing, so there's no dependence on the y. As the y changes, the equation doesn't care, which means there must be no y in it. I like it. All right, so that's an easy one. Anytime you see a cylinder, which is basically a shape repeated along some axial direction, then it must be missing that variable. This one is a little evil because it's just like those. They don't stop. This one also doesn't stop. And look at the XZ plane. What do we say about the XZ plane here? As where am I at? Here. And the XZ plane is supposed to be hyperbolas. In the YZ plane, it's supposed to be these parabolas as we move away.
The parabolas is wrong in the YZ.
Say again?
The parabolas are supposed to open up in the Y direction. Okay? YZ.
So this one again, if I draw for k equals 0, I got this guy.
No, you should open up in the Y direction.
How do you mean? What do you mean? What if let's see.
Because Z is acting like what we're used to X being. Right? And then Y is, we're used to it being the high. So it opens down in Y direction.
So, for example, if z was 1, then y would be -1. If z was -1, then y would be -1. Yeah. Okay. Why did I draw it the other way? That's useful. What was I thinking about? Oh, okay. All right. I was looking at it. Okay. So now as I move away from, so this is the x equal to 0. And as I move away from that plane, in either direction, this is going to go up. See how I say? So like if I wanted to do the trace for k equal to 1. So let me see, make sure if I say k equals to 1, what is that really that I'm doing? Letting what be 1, really? What's my control in this part here? X. I like it. So I'm just investigating planes that are parallel to the YZ plane. I like it. And I like that. That's right. It had this drawn the entire wrong direction, which really makes it a lot more difficult than it had to be. So k equals 1, if I want to draw this, that would be y equals 1 minus z squared. So it's just this guy picked up by 1 in the y direction. So now if z is 0, y is 1. But now this is kind of like this trace here is sitting out away from the YZ plane. It's 1 above the YZ plane. And the same thing would happen if I went for k equal to negative 1. So as I move away from the YZ plane, it's pulling back in both directions. I like that. So that, yeah, then it becomes a lot easier to see that it would be this. As I move away from the, well, not this one. Let me see, where was it? Yeah, that's the one.
Oh,
Okay.
graph, yeah,
Yes,
graph
it
D is the
D is
solution
that.
of that problem.
Sweet. I like it.
I just want to understand why, you could get that visualization of it, because it was kind of hard to translate it over from the traces.
Oh, so for example, what do I want to say here?
You're saying that the